Hello, students. In this lecture, I am going to explain what will happen if cryogenic liquids, that means liquids of two different boiling points, need to be transported through pipelines. And if there is a chance of mixing, then what happens? What are the problems? And problems may be such that it will be difficult to transfer cryogenic liquid through that pipeline, and sometimes accident or there may be oscillation, knocking in such an extent so that everything can collapse. So we need to know this, and here it will be clear to you what will be the strategy so that this type of problems won't be occurring. So particularly this I'm going to explain with respect to transportation of liquid propane and liquid butane, because they are the main constituents of LPG, liquefied petroleum gas. So liquefied petroleum gas, uh, okay, before that, let me give some idea about the boiling points of cryogenic liquids and their volume expansion when they are converted to gaseous forms. So oxygen, uh, its boiling point is minus 183 degrees Celsius. Volume expansion is 1 is to 860. That means 1 liter of liquid oxygen will be converted to 860 liter of gaseous oxygen. Similarly, in case of nitrogen, boiling point is minus 196 uh, degrees Celsius. Volume expansion is 1 is to 696. For methane, at boiling point minus 162, volume expansion is 1 is to 579. For helium, minus 269, and volume expansion is 1 is to 757. For argon, this one. For hydrogen, minus 253, it is 1 is to 851. For fluorine, minus 187, it is 1 is to 888. For propane, that cryogenic liquid of our interest right now in this current slides, is having a boiling point of minus 44 degrees Celsius, and volume expansion is 1 is to 274. So you can see that for both the cases, volume expansion is about 250 times with respect to the liquid state. Their specific heat uh, is, of course, in case of propane, it is 0.39 calorie per gram per degree Celsius. Latent heat of vaporization is uh, uh, enormous, 428 kilojoule per kg. Flammable limits is very, very low, so it is highly flammable. Auto ignition temperature is 466 degrees Celsius. For butane, also you can see almost similar specific heat. Latent heat of vaporization is also comparable. Flammable limits is also low, so highly flammable gas. And auto auto ignition temperature is 405 degrees Celsius. Uh, Actually, this flammable limit is low, that means at low concentration it is flammable. Above, so this is lower flammability limit and upper flammability limit. So above 8.4%, it is not flammable, uh, uh, but as that much concentration won't be prevalent everywhere. So at the boundary of that gas air mixture concentration, if it is within this range, it is flammable and that flame can be propagated. So, though this lower flammability limit and upper flammability limit is within this range, still it is highly uh, fire hazards, both fire and explosion hazards. So now you can see different types of two-phase flow, uh, bubble flow, flash flow, stratified flow, wavy flow, slab flow, annular flow, dispersed flow. So see, these different types of flow is there, and out of all this flow, this normal flow and dispersed flow is that means we can allow, but all other flow will be bubble flow also to some extent is not that much bubble flow, fluff flow. But this one, slug flow and this one, annular flow, stratified flow, wavy flow, these are very, very dangerous with respect to pipeline transportation of cryogenic liquids. So you can see this particular diagram is explaining what will happen if suddenly means, one cryogenic liquid is allowed to flow through a pipeline where temperature was not uh, lowered prior to its flow to a sufficient level where the liquid won't be boiling. So as soon as it will be coming into contact with high temperature, so you can see that this is point vapor, then liquid annular, mixed slug and annular flow. End of slug flow is here. Slug flow regime is this one. So here you can see coalitions of the bubbles begins. This is the formation of permanent bubbles. Boiling begins. So from here itself, here you can see that flow is normal because that heat transfer is not that much, so that some liquid has been converted to vapor form. So if we could maintain temperature below its boiling point, then the flow of the liquid will be normal. So here, this particular diagram with respect to these two numbers is nicely explained to show the different regime of flow based on these two parameters. So it is explanatory. This is known as Baker's diagram. With respect to this Baker's diagram, we can determine the regime of flow, and accordingly we can take actions. So mixing strategy of liquid propane and butane will be this one. If both are of the same temperature, they can be mixed at any proportion as there is no change in phase or volume. But if they are at their normal boiling points, liquid butane can be mixed gradually with liquid propane, though there will be generation of vapor it will be under control and flow will be in dispersed flow regime. So that's why you should follow this strategy because in that condition, flow will be under our control. So the piping measures, the main aim of the cryogenic piping insulation system is to create a vapor barrier to keep atmospheric moisture from leaking into the insulation space. This moisture permeates insulation and then condenses, which significantly increases the corrosion changes in the lines. Also, buildup of water or ice may occur, which in turn results in lower performance. Whenever the insulation has been compromised, the thermal efficiency is lost and energy consumption increases. So, high energy consumption can be reduced by using adequate insulation materials. The vapor barrier system must keep atmospheric moisture from entering the insulation space and freezing against the cryogenic line. So these should be the measures. So cryogenic liquids generates a large volume of gases when vaporized. So if they vaporize inside a sealed container, the container can burst due to the enormous pressure. As a result, this cryogenic piping requires special types of material, supports, and valves different than that of normal piping systems, which makes the design of cryogenic piping system highly critical and challenging. Some of the cryogenic piping system requirements are sufficient flexibility as with lower temperatures, the material contracts, creating huge thermal stresses, which must be compensated using proper flexibility. All cryogenic lines are insulated to avoid heat gain from the environment and for safety. All these increase the weight of the pipe in the making of cryogenic system more rigid. So with that, let me conclude my talk. Thank you.